Thank you for the introduction, and thank the organizers for the invitation. I want to talk about degenerations of rational maps and hyperbolic components. So let me tell you sort of the overview of this mini course. And what type of questions we want to understand and how to study these type of questions. All right, so we are interested in one complex dimensional rational map. So a rational map for me is always a map on the Riemann sphere. So it can be written as the ratio of two polynomials. Where all the coefficients are in complex numbers. The maximum degree of the two polynomials is d, and we do not have any common factors. Right? And if we write the space of all such rational maps into a set, then this is an open subset of the projective space. The space of Mobius transformation acts by conjugation. And its quotient is the moduli space. Thank you. This moduli space is not compact, and then we say a sequence Fn, a conjugacy clause of rational map, is degenerating if this sequence goes to infinity in MD. Right? So in other words, it escapes every complex set in MD. We are particularly interested in a special type of rational maps called hyperbolic rational maps. So F is hyperbolic if for every critical point C under iteration, this critical point converges to an attracting cycle. All right, so this is easy to see. It's an open condition, and they form an open subset, and then it descends to, and it's invariant under Mobius conjugation. So we can define a conjugacy clause of a rational map being hyperbolic. It is conjecturally open. It is conjecturally dense in the set of in this moduli space, but this is still a conjecture, and it's equivalent to sort of in the degree 2 polynomial setting. It is equivalent to the Mandelbrot set being locally connected. All right, and the type of object that we are interested in is called the hyperbolic component. So a connected component of hyperbolic maps is called a hyperbolic component. All right, so let me give you some examples. In MD, usually. But I think this, we can study these hyperbolic components in various algebraic subsets of red D. For example, we can also consider the hyperbolic components when we only restrict ourselves to polynomials and things like that. All right, so this is supposed to be the Mandelbrot set. This is the set for quadratic polynomials where in the parameter space C, for which the Julia set is connected. And all these bulbs you see in this picture, they are hyperbolic component. Right, so one important feature about hyperbolic component is that as we vary our map in a single hyperbolic component, its Julia set, the topology of the Julia set remain constant. Only the geometry change. So if we pick, for example, a point here, this map is f of 0 of z, where the map z squared, the Julia set is going to be a circle, a round circle. And if we pick any point inside of this main cardioid, the Julia set would still be topological circle, but it might be it have different shape. So the question that we want to understand is what are the topology or the shapes or the geometry of these hyperbolic components when we look at these hyperbolic components in higher degrees of rational maps. Right, so the type of questions that we want to understand, for example, the boundedness of hyperbolic components. For quadratic polynomials, we know the hyperbolic component is bounded if and only if it is not this escape locus where the Julia set is a Cantor set. And then we want to understand this type of questions for general rational maps of higher degree. Or if we want to be more ambitious, we want to understand how a hyperbolic component can degenerate. All right, and sometimes in the case when we study the moduli space of polynomials, if you have connected Julia set, then these hyperbolic components are bounded. But we also try to understand what can we say about its boundary. So here H stands for a hyperbolic component, and how different hyperbolic components interact with each other. Again, going back to this quadratic polynomial setting, we know each hyperbolic component other than this escaping locus, the closure is going to be a closed ball. And for this main cardioid, there are countably many hyperbolic components that share a single point of bifurcation. So these are the type of questions that we want to understand in higher degrees and higher and for rational maps. Yes?
So when you say interact, what did you mean by interact?
Well, I'm putting this question in a vague format, which is why, I mean, one of the questions that we want to understand is when you have two hyperbolic components, when they have a non-empty intersection closure. Right, so, or you can put it in a slightly different way. If you know when you have a hyperbolic component, and then there is some meaningful transition from maps from one hyperbolic component to the other. Can we describe such bifurcation? Can we describe when, if you have a hyperbolic component, main hyperbolic component, what are these other hyperbolic components that share some points on the boundary?
Topologically, can they link in some way?
That's a good question. I don't know in general. It looks possible, so I will probably talk about some results related to the second question. For example, in higher degree, their closure are no longer going to be closed balls. So, so they can have some self-bumping occur, and then these hyperbolic components lives in a higher dimensional space, and a lot of things can actually happen. So I don't know. All right, so well, what are the strategies to understand these type of questions? So at least for this first boundedness question, this strategy was motivated by Thurston's proof of the Thurston's compactness theorems for the deformation space of asymmetrical convex co-compact three-manifold. So it consists of two steps. For this mini course, it's not important to know this definition, but I'm trying to draw a parallel about our approach to the original Thurston's approach. The first step is to construct some something geometric and try to construct some limiting map on a tree. And the second step is sort of topological and combinatorial, which use this limiting map on the tree to get some kind of a decomposition of the original rational map in terms of something related to the limiting Thurston obstruction. Right, so we'll talk of two important steps for studying these type of questions. We want to construct some limiting map on a tree, and then we want to understand how this limiting map on a tree gives some kind of a decomposition. All right, so I think the mini course will probably consist of two parts. The first part is to give you a construction of this limiting map on a tree. So I will talk about a geometric construction and an algebraic construction, and they will turn out to be the same, equivalent. But the important thing here is that I think each construction has its merits, and sometimes it's better to think about in a geometric way, and sometimes it's better to think about this in the algebraic way. I will also talk about this connection with something called the rescaling limit. Or the length spectrum for this degenerating sequence of rational maps. highlighting an important difference, some important differences between when you study sequences versus families. There are some subtleties and there are some differences when we study sequences of degenerating sequences of rational maps versus a holomorphic family of rational maps. And I want to talk about some of the differences there and how to deal with these subtleties using something called like a cascade of Robinson's field. And then this would actually be, in some sense, essential even when we try to understand some of the simplest examples of the boundary of the hyperbolic components. And the part 2 of this mini course will focus on some applications, and then we'll start with something in degree 2, or in the bicritical case, where we have only 2 critical points, and we can, based on the work of Zhang Kiwi, we can almost classify those. We have a very satisfactory classification of this limiting map on a tree, and how that can be used to solve some boundedness problems for quadratic rational maps by the work of Hongming, Kevin, and Adam Epstein. And then I will talk about what happens in degree 3, where, or degree greater or equals to 3, where things just get exponentially more complicated. I'll give you some examples to illustrate why the similar method in degree 2 would just not work in higher degrees. So we need some geometric control about the post-critical set to actually say something. And I will talk about 2 different sources of this uniform geometric control. The first is a special type of degeneration called a quasi-PCF. And the second source of this uniform geometric control comes from some a priori bounds from renormalization. And how in these 2 cases we can get a very satisfactory decomposition theory for these rational maps, and then we can interpret this limiting tree as the dual to some Thurston obstruction, and then we will conclude by some contradiction, and then we show the hyperbolic components are bounded. Right? So the strategy is to actually, I forgot to mention that, the strategy is try to prove by contradiction, and we assume it's unbounded, then we can extract some degenerating sequence of rational map, and in which case we will obtain some limiting map on a tree, some decomposition, and the final punchline is to show such decomposition would not exist. And that's the general strategy here. All right, so let me start with the first part and then tell you something about this construction. And so this goes down. And this goes up. All right, so this is, let me first start with this geometric construction, and it's related to the barycentric extension. The idea is to first construct an extension of a rational map from the Riemann sphere to itself to a map on the hyperbolic 3 space, and then we degenerate the hyperbolic metric. And it turns out that this construction is equivalent to something more algebraic, and then perhaps the audience in this room are already more familiar with the other construction using Berkovich space. And I'll show, explain the connection in a moment. All right, so what is this barycentric extension? Well, here we are identifying the Riemann sphere with S2, and we think about this S2 as the boundary of the hyperbolic 3 space. Right, so this is the Poincaré-Boas model for the hyperbolic 3 space. And whenever we have a probability measure on S2, let us assume without atoms, we can define the barycenter for this probability measure, and let's denote this by beta of mu. Let me denote the origin of the ball as this O. Then the barycenter of this measure equals to O, the origin of the ball, if and only if, when we take the integral over S2, this integral is going to be 0. So here, we are thinking about a point in S2 as a vector in R3. So we are taking the integral with respect to this probability measure of this vector in R3, and then this condition says that this total integral is going to be the 0 vector here. All right. And if you, this barycentric extension is supposed to be conformally natural. So if you have any point x, what we can do is to construct a map, isometry that sends 0 to x, and the barycenter of mu is x, if and only if the barycenter of the push forward of so G goes the other way around. The barycenter of the push forward of G of this measure mu equals to 0.
So G is your isometry, x to 0.
Yes. G is the isometry that sends x to 0. All right, and then one can define the important feature, which is a very classical theorem by Duardi and O in dimension 1. But it can be generalized, the same argument generalized in higher dimension, which was included in the Haber's Teichmüller theory book. And Peterson's paper that the barycenter exists. There is a unique barycenter for mu. Right, so mu, as long as mu satisfies these conditions, mu is a probability measure on S2 without any atoms, then there is a unique barycenter for this measure.
Wait, what was the integral? What are we integrating?
This one? So this C is a point in S2, which you embed in R3. So this is a vector, and we're integrating this vector over this measure. Right? So this is an integral of basically a integral in R3. Yes.
So why is it important that the measure doesn't have atoms?
Well, it is not very important that the measure doesn't have atoms. It's whenever you have an atom with, let's say, mass, I don't know, bigger than 1/3, then there might be multiple different barycenters. So to avoid such examples, I'm just going to assume that this probability measure does not have any atoms. But you can still have some atoms as long as the mass of the atoms is not too big. Yes?
So what does the theorem say? So that you have a mass beta that goes from Roman measure to S3 such that it's 0, then
Can you write it? What does the theorem say?
Okay. The theorem says that if mu is is a probability measure without atoms, then there exists a unique x such that the integral of S2 for when you take the push forward of the push forward by g of this measure mu at zeta equals to 0. And then g, since g is in the isometry of H3, and since x to 0. So the g is not unique. G is only unique up to post-composition with something that fixes the origin. But that is that subgroup, the stabilizer of the origin is SO3. And the SO3 acts on this thing by linear map, so it fixes the 0 vector. Right? So maybe, I mean, this is some observation that one can take if G is in SO3, then this integral of S2, the of G push forward of mu as zeta is simply G acting on this integral. Right? So if it is 0, then it is 0 if and only if this integral is 0. All right, so now let me tell you the definition of the barycentric extension. So F is going to be a rational map of degree D. Then we want to extend this map to a map from the hyperbolic 3 space to itself. Well, how do we do that? Well, if you give me any point x in H3, so here is the picture. The origin here, and I have a point x. I'm going to first look at an isometry that sends 0 to x. So x is going to be mapped to the barycenter of the push forward by f of the push forward by m of the probability measure coming from the usual metric on the sphere. Right, so this mu of S2 is the probability measure coming from the metric on the unit sphere. And I'm going to push forward by it using this isometry. And then you see the difference is there are a lot of choices of this mx. The difference is by a precomposition of something in SO3, but SO3 makes this the standard metric or the standard measure invariant. So this is well defined. And then we push forward by f. And then we take the barycenter. Right? So in other words, you can think about this barycentric extension is defined implicitly by some integrals. So you're taking the integral of over S2 of my, where you take the inverse of f of mx of zeta d mu S2 of zeta here. And then this whole thing equals to the 0 vector. All right, and then from the construction from this implicit definition, one can easily see that this barycentric extension satisfies some nice properties. This is smooth. And it is real analytic, in fact. In fact, real analytic. And it is so-called conformally natural. So that is, if I take the barycentric extension of M composed with F composed with L, where M and L are Mobius transformations, then this is going to be the same as taking the composition of M with the barycentric extension of F composed with the barycentric extension of L. Right? So it's a generalization of the usual Poincare extension for a Mobius map to an isometry of H3. Right? But I also want to remark that it does not respect iteration, which is a bad thing when we want to study the dynamics. But that's not too bad. The difference between the extension of the second integral of f and the iteration of the extension is differed by a finite amount, by a uniformly bounded amount. And if, as we want to scale some metric, this bounded amount goes to 0. So we, in the limit, as we were going to take in the second step of this construction, the extension, the limiting extension would actually preserve has this nice property. This. All right. So this construction actually also works in any dimension. So in dimension 1, that is, if we have a map on the circle, we can also use a similar definition to define a map on the disk. So if F is a map from circle to itself, let's say the restriction of a Blaschko product then the same formula applies to extend the map to a self-map of the disk. And it turns out that this extension is indeed the original map you start with. Right, so in dimension 1, the barycentric extension of a Blaschko product is the Blaschko product. And then we know that Blaschko product satisfies some nice property. So for example, it has Schwarz lemma. EF, or maybe the derivative of EF, is bounded by 1 with respect to the hyperbolic metric. And for this barycentric extension in dimension 2, we don't expect we have this uniform distance decreasing property, but it's not too bad. So there is a theorem which says that we can control the derivative of the barycentric extension. It's always bounded by some constant times d. All right, and then the conjecture is this constant c equals to 1. All right, and I'll show you some example in a moment just to give you some idea about this barycentric extension. And
sorry, just to clarify, when you're saying norm, you mean in the hyperbolic metric?
yeah.
Now on H3 is what you're saying.
Yes. So the derivative, the norm, is computed with respect to the hyperbolic metric. The constant is universal. It doesn't depend on anything. So for now, I think the constant, you can make it to be 12 or something, but I expect the constant to be 1. So, but this derivative, indeed, the norm depends on d. That's the important part. When d, I mean, as you can see, if d equals to 1, then this barycentric extension is really the Poincare extension, and then it's an isometry. Right? And no, you don't need f to become formal. F, for this bound. For this bound, you can still get some, if f turns out to be quasi-conformal, and it has some quasi-conformal constant k, then this constant c would depend on k. But you still have some control in terms of the conformality of the map f. But in order, if you want to have a universal c, this map has to be conformal. All right, so
If you do just z to the d, the simplest, do you get that it's exactly what
this is exactly what I'm going to do. I mean, basically, this is the only example that I can say something about the barycentric extension on the nose. So usually when we work with this barycentric extension, you can have some nice property, as I'll explain in a moment, about the quasi, everything is up to a bounded constant O of 1. So for the barycentric extension z goes to z to the d, we can say something more precise. Right, so if we look at this map, z goes to z to the d, then we have two super attracting cycle, fixed point, 0 and infinity. All right, and then by the symmetry of this map, what one can conclude is that now you have this ball with the radius centered at 0 with the radius r. Or maybe this is the sphere or the boundary of the ball centered at 0 with the radius r. And this circle bounds a totally geodesic plane in H3. Right? So when r equals to 1, this is the equator, which bounds this totally geodesic plane. And the important feature here is that this ball, or this sphere, or this circle, is mapped to the boundary of the circle centered at the origin with the radius r to the d. Right? And when you look at this geodesic connecting 0 and infinity, this geodesic is totally invariant under the map, the barycentric extension of z to the d. And on this geodesic, the map is simply expanding by a rate by the linear factor of d. So along the geodesic, the derivative, the norm of the derivative equals to d. Right, and then we expect this is the worst case scenario. And for all the other rational maps, when you extend it, the norm of the derivative cannot go beyond d.
Excuse me, if you take an invariant measure for the d, is the barycenter 0 or not? You said it's not compatible with iteration.
Yes.
So it's still true that the barycenter is 0 from the measure?
For z to d, I expect this might be true, but I don't know for general ones. Because of this symmetries, I think it might be able to conclude something about the barycenter of any invariant measure. But I don't know about the general situation. Yes. It's not going to be the composition of the two. Yeah. So only for degree 1 maps. You can break down the.
You said something. You said that when I take the second iterate, then the difference is bounded.
Yeah, the difference is going to be bounded by all of 1.
Yeah, and it's the same under composition.
Oh, you mean the question is about the all of 1 estimate? Yes, the all of 1. This all of 1 would depend on the degree. So if you compose two maps with the bounded degree, and then the barycentric extension is going to be bounded. All right, so okay, so I want to now talk about so this bounds on the derivative allow us to, it's an equal continuity result. But in order to bring all the things into inside, we want to find some degenerating scales, and we try to do some sort of a rescaling limit of these hyperbolic spaces. All right, so now I want to talk about degenerating scale. So we are going to associate a number for each rational map and a number for each conjugacy clause of a rational map. All right, so I'm going to denote that by R of f, and that is going to be the maximum of the hyperbolic distance between 0 and one of its pre-images. Right? So this map, the barycentric extension map, turns out to be a proper map. So the inverse image of a single point is compact, and the maximum is obtained. So I'm measuring the distance between 0 and then one of its pre-images of y, of 0, the origin here. And I'm going to define R of f, the conjugacy clause, as the infimum over all x in H3 of the maximum of y in the preimage of x, the hyperbolic distance between x and y. That's a good question. I don't know. Is EF a discrete set? Is a discrete map? Discrete map means it's, the preimage of every point is a discrete set. I know it's proper, so it's a compact set, but I don't know if it's a discrete. If it's proper and discrete, then you can define the degree and so on.
Why determinant? EF minus 1 of 2. That would be low.
Well, I think you can actually prove that it is non-empty, but I don't know how to do that on the spot. It's non-empty, and the map is on the H3 is surjective. I think you can prove that, but it's not too hard to show that. But I don't know if the map is discrete.
This is an extension, right?
Yes.
So if you go to the boundary, you recover the map.
Yes.
On the boundary, it's topological degree.
Yes.
And the map is proper.
Yeah, so the map must be surjective. I think that's the argument. Thanks. All right, and an important feature about this degenerating scale is that this number detect is a proper function on the moduli space. So R of f goes to infinity if and only if f goes to infinity in red D, and R of f goes to infinity if and only if the conjugacy clause goes to infinity.
So is there a theorem or it's an observation?
This is a, let's put a theorem. And then there's also a theorem by a recent observation or theorem by Charles and Guillaume, which says that R of f is compatible with the absolute value of the logarithm of the resultant.
Going back to the definition over the conjugacy class.
Yes.
I thought you were going to say infimum over all f conjugate to f, in the conjugacy class. But I guess that's the same.
That's the same as a choose. Yeah, exactly. So that's the same as changing the base point from the origin to any point in the H3, because of the conformally naturality of the extension.
Can you write the formula relating this to R? So what is R, the conjugate space, the infimum of R f over the conjugate space?
That's also true. So this is also the infimum of f in, or g in the conjugacy clause of R of g. But because of the conformal naturality, we can just pick one and change the base point. Right, and then this holds if, like, let's say R of f is greater or equals to 1. So to get rid of some The modularity?
The regularity.
The regularity is a real analytic. Yes. The resultant of f. So log of the absolute value of the resultant of f. Right. So I mean, from this theorem, it's a corollary of this theorem that this map is a proper map. All right, and now I want to, okay, so the idea here is now, instead of working with this barycentric extension on H3, we want to work off this barycentric extension. So if I have a sequence of rational maps, and then we can look at the sequence of extensions, and then we want to, instead of thinking about these as maps from H3 to H3, we want to think about these maps from H3, but with the rescaled metric. To itself. Right, so here I'm going to assume this Fn satisfies all of Fn is greater or equals to, or this is inf, so it's less than or equals to all of the conjugacy clause plus 1. Right, so it's almost minimized. We almost choose a nice representative so that this rescaling or this degenerating scale is comparable with the degenerating scales associated to the conjugacy clause. Right? And one nice thing about this metric space here is that if you rescale your hyperbolic metric, the metric becomes more and more negatively curved, and then in the limit, you obtain something like a tree. All right, and then to formulate this properly, one way to do this is to construct something called the ultra limit. And to do that, we need to construct it with something like an ultra filter on n. So what is an ultra filter on n? So this is a finitely additive probability measure on n that with a taking value in 0 and 1. All right, so example, we can take omega of A of a finite additive probability measure to be equals to 1 if this small a is contained in the set A, or 0 otherwise. So say for every a for any real number, for any natural number, we can define this ultra filter, which simply output 1 if a is in the set, or 0 otherwise. So in other words, this is a dictator. A is a dictator, and then as long as a set contains A, the set is 1, and otherwise the set is 0. Right, such ultra filter is called principal, and any ultra filter that is not principal is called a non-principal ultra filter. And the existence of non-principal ultra filter is guaranteed by the zones lemma. So, but it is not easy, or I don't think it's possible to construct one by for a non-principal ultrafilter. And I know many people have strong opinions about the election systems and the existence. I mean that is equivalent to say that there is an Arrow's impossibility theorem, which is equivalent to say that there is no non-principal ultrafilter if the set is finite. But since we're working with the infinite set, the set of natural numbers is infinite, there is a non-principal ultrafilter. And so maybe all the things can be resolved if we have infinite many people. All right, so given an ultrafilter, we can define a lot of limits. So now we're going to fix a non-principal ultrafilter, and then we can define limit with respect to the ultrafilter in any metric space if the set of n such that if for every epsilon, this is really the most natural way to define the limit, the set of all natural numbers, so that the distance between xn and x is less than epsilon, is a very big set. So the omega of that is 1. And the ultrafilter satisfies, this limit satisfies a lot of nice things. So if x is compact, the limit always exists. So you don't need to pass to a subsequence. And another important feature is that this limit is contained in is an accumulation point. Non-principal one. All right, and then using these conditions, we can properly define the ultra limit for such rescaled hyperbolic three spaces, and it will converge to something called an R tree, and this R tree turns out to be equivalent to some Berkovich space, and I will talk about this in the next lecture. I'm sorry for running over time.